So let's see here. We can obtain the electric field E from V, from the potential. Okay, you know, E is a vector and V is a scalar. Generally speaking, a scalar is easier to calculate than a vector because it carries no sign, no direction. Okay, it only has positive and negative signs. Now, you know, from E we integrate, we get V, right? So what is the inverse of integration? Well, we differentiate, right? So when you take V, we differentiate, we get E. Let's see how one might do that. Okay, let's first look at the one-dimensional case. Look at the general expression first. Here is the general expression. Let's recall. Initial minus V final. It's like this. Okay, so in the one-dimensional case, okay, if you wish to start with one-dimensional case, I would write it as V. Let's say it's an x direction. Okay, so V as a function of x minus V whatever value. Okay, whatever value, and you know, certain point. Okay, at a certain point, you know, we call it V naught. Okay, and what is that equal to? That equals to this initial here. So this is x. Okay, and here's final point. We call it x naught, corresponding to the potential V naught. E dot ds in one direction, in one dimension, in the x direction, this is just ex, the x component of E times the x, right? How does one calculate Vx based on Ex? All we have to do is to integrate, okay, over Ex. How does one figure out Ex once you know Vx? Well, we know naturally we have to differentiate. So let's differentiate both sides with respect to x. So the first term will give us dv over dx, right? And let's see what happens if you work that out. Okay, this is x over from x to x naught. So we can put a negative sign and reverse the order, x naught to x, and then ex dx. And don't forget, I have to differentiate that. Okay, we all know from the basic theorem calculus what that is. Okay, so what is that? That is negative Ex. That's it. Alright? So, I learned that Ex, the x component of the electric field, is just negative dV dx. See, once you know V as a function of space, all we have to do is differentiate it with respect to the x variable and take a negative sign, I get the x component. So similarly, how does one calculate the y component of the electric field? So what's Ey? What is that equal to? Well, if you do the same similar calculation, you will get negative what? dv dy, and so on, right? Now, in general, V can be a function of both x and y. In fact, can be a function of x, y, and z. All right. So when you do a derivative for a multivariable function, the proper symbol to use, as you know, is the partial derivative symbol. So we're not going to use dv over dx anymore. Rather, more carefully, we're going to do this: negative partial v over partial x, partial derivative, right? And here's the same thing: negative partial v partial y. And for the z direction, something similar. So, what is the most general expression for the electric field based on the knowledge of the electrostatic potential? Well, E is what? EXI plus EYJ, that's the y component, plus EZK, right? The z component in k. Now, x direction, negative partial v partial x. So it's negative partial v partial xi, alright? And then minus partial v partial y j, and then minus partial v partial z k. Now, as you recall from your calculus class, I can write this as the gradient operator, negative gradient v. So finally, E, the three-dimensional case, E equals negative gradient v. This is how you get the vector E field from a scalar V field. Okay, so if you know how to calculate V, then all you have to do is take the gradient with a negative sign. You will get the electrostatic field, the full three-dimensional vector expression. The gradient operator, we're going to use that a lot later. So what you learn in math will now prove to be actually useful. Okay, so much for the basic concepts. Now let's take a look at the first example. Let's revisit the so-called electric dipole. We learned in the first chapter what an electric dipole is. Basically, it's a pair of charges, positive Q and negative Q. They are separated by very small distance a. Okay. In chapter 23, we learned to calculate the electric field at a point P along the line or the x-axis joining these two charges. Okay. And that point P is a distance x away from negative charge, and x has a much greater magnitude than the separation a between these two charges. We learned how to calculate the electric field there, if you recall. Now, we're going to revisit this problem from the electrostatic potential point of view. Namely, we're going to calculate the electrostatic potential at point P produced by this pair of dipoles. And then we are going to use that knowledge of the electrostatic potential to calculate the electric field, and you will see that it should agree with what we got before in chapter 23. Okay, so let's calculate V at point P. Now, V in this case is the sum of two terms, one due to the negative charge, the other due to the positive charge, right? So we can easily find that for the negative charge, I have negative k q over that distance, which is x, right? This is the electrostatic field for a single point charge, a distance x away from its location. And then from this guy, I have positive kq, same q, but the distance is different. From here to there, that distance is actually x minus a, because this whole distance from here to there is x. So it's x minus a. Okay, now we can always do a little simplification. X times x minus a, kq, and here is x minus a, and then minus x. So it's overall you have an a here. Okay, if you work out the algebra. All right, now we wish to simplify this, knowing that a is far less than x, so it's x minus a is roughly just equal to x, so the denominator is roughly x squared, so I can write this as k q a over x squared. And q, as you know, is just dipole moment p, so this is just k p over x squared. You know, for a single charge, the electrostatic potential decays like 1 over distance, but for a dipole it goes like 1 over distance squared. Okay, so this is expected because the dipole is made of two charges that are opposite to each other, so it decays faster. Once we know that, how does one calculate the electric field produced by the dipole at the point P? Well, we're going to use that formula we just developed. E, everything is in x direction. Okay, so E, just only has x component, E of x. What is that equal to? Negative dv dx, right? The x component, don't forget the negative sign. Okay, so it's negative d dx of kp over x squared. Okay, one can easily finish this in this derivative. The derivative of x to the power negative 2. When you take derivative, you get negative x to the power negative 3. The negative sign cancels. You get positive kp. There's a 2 here. X to the power negative 3. And this, check your notes for chapter 23. It agrees with what we got before. Okay, so you see we have an alternative way now to calculate the electric field. That is, we don't deal with the vector electric field directly. Rather, we first figure out the scalar electric potential. And then we take a derivative. Okay, we take the gradient. We can find the corresponding electric field. Now, of course, just like what we discussed in chapter 23, this expression can be obtained without going through all this simplification. Rather, what we can do is take the derivative. Okay, take the derivative. So, and that means we recognize that this field and that field differs only by a small amount, so that we can expand the second term in in Taylor series. So Vp equals the sum of these two, right? The sum of these two. If the first one is we call it V1, okay, V1x. And what about the second one? Well, first of all, the second one is opposite to the first one because it carries an opposite sign of charge, so it's opposite v1. And the second difference is instead of x, I have x minus a because the distance is now shorter. So x minus a, right? And then expand the second one. Okay, expand the second term. The second term is roughly equal to, copy the first term. Second term is roughly equal to v1x, and then plus dv1 dx times negative a, right? Negative a, because it's x minus a. All right, v1x, v1x cancels, so we're left with, what do you get? Negative, actually negative cancels. dv1 dx times a. What's v1? v1 is the electrostatic potential carried by a single negative charge here. So in our case, that is a times d dx of v1 again. v1 is just right here, okay? Just that term. Negative k q over x. Okay, now finish this calculation. 1 over x, you take derivative, what do you get? You get negative 1 over x squared. Negative cancel with that negative sign, so overall you get k q a over x squared, and that of course agrees with our first expression. So this is the example of the electric dipole revisited with the knowledge of electrostatic potential. Okay, our next example, example 2, is quite simple, but is widely used in actual devices. What we have here is what's called a parallel plates setup. In other words, we have a piece of flat conductor, another piece of flat conductor. This one is charged to a surface charge density of positive sigma, and that one is charged to the opposite surface density of negative sigma, right? And they're separated by distance d. We can consider the size of each plate to be virtually infinity. In other words, the linear dimension of each piece is far greater than the separation between them d, so we can consider each piece as almost infinity. That would simplify our calculation for the electric field. We all know how to calculate the electric field in between these two plates. The question now is, how does one calculate the electrostatic potential distribution between here and there? Let's say we draw an x-axis. Okay, we draw an x-axis, and here is the negative, here is the positive. So it's a little awkward, but I'm going to draw an x-axis like that, starting from negative, going that way, because that way the electrostatic potential will increase as you move away from x. Now, what is the electrostatic field? Well, we can easily calculate that. Suppose you have a point here, a distance x from the origin. The electrostatic field at this point is the sum of the field from this guy and the field from that guy. Okay, the field from this guy points backwards. And how much is that equal to? You recall, it's sigma over 2 epsilon naught. Right? That is the field produced by a sheet of an infinitely large sheet of charge, of charge density, of surface charge density sigma. In fact, it has a negative sign, okay, because it points backwards. On the positive x-axis goes that way. Meanwhile, what is the electrostatic field produced by that guy? Well, it pushes away because it's positive and has the same exact magnitude. Okay, so again, it points that way, it's negative, and has the same magnitude, negative sigma over 2 epsilon naught. This, the sum of these two, is the electrostatic field in between these two plates, and then that is equal to negative q sigma over epsilon naught. Now, you notice that we can obtain the exact same result from a slightly different view. All I have to do really is draw a Gaussian surface like this. If I draw a Gaussian surface like this, it's like a cylinder, okay? This is only the side view. There is a top side, there is a bottom side. Okay. Now, the bottom side is entirely within this metal plate. So what is the electric field on the bottom side? Well, it's 0, okay? Assuming it's ideal conductor. And the electric field goes along the x direction, so it doesn't penetrate the side of the cylinder. It only penetrates the top side, the top of the cylinder, okay? So, just like how we calculate the electrostatic field outside an ideal conductor, if the area of the top is A, then the flux is E times A. It's the flux through the entire cylinder, not just through the top, because there is no flux anywhere else. And that equals charge enclosed divided by epsilon naught. Okay, and the charge enclosed is sigma times the same area A, is the same area A, sigma A over epsilon naught, and therefore E equals sigma over epsilon naught. That is the magnitude. Okay, and as far as the direction is concerned, we pick this to be positive x direction, and since the actual E field goes backwards, it's negative. It's just the same as that. Okay, either way you get the same result. One through superposition of two plates, the other direct calculation with Gauss's law. Now, once you know the electrostatic field, what about the electrostatic potential? Well, this is a simple case because the electric field is not a function of x; it's a constant. Okay, it's uniform, and so we can establish an electrostatic potential distribution like this: V initial minus V final. Let's find the general formula first. Initial to final, E dot dx, E dot ds. Right? That's the general formula. Now, in our case, we are going to, let's say the final the initial position is x, or just let's say the initial position is here. Okay, let's say the initial position is here, v naught, and the final position is at a certain location x. Okay, now what is that equal to? Initial is 0, so x equal to 0. Final is a location x. E dot ds. Now, as we go from here to there, we are going this way. This is a positive x direction. The actual E field is negative x direction. So don't forget there is a negative sign. Okay, E dx. Okay, this negative sign again is because E points along the negative x direction and ds points along the positive x direction. So this calculation is very simple because E is a constant. Okay, E is a constant. I'm going to take that out. Dx. So it's just negative Ex. Okay, E itself is sigma over epsilon naught with a negative sign. So I got V naught minus Vx equals to negative E. Actually, be careful here. This is the absolute value of x. Okay, absolute value of E, right? Okay, because it's magnitude of E times the magnitude of ds times the cosine theta. Cosine theta is negative 1. Okay, so be careful. I must use the absolute value of x, which is not, there's no negative sign anymore. It's just sigma over epsilon naught. So negative times the absolute value of E, which is sigma over epsilon naught. Okay, and then times x. Now, V naught is the potential at that point, which I usually define as 0. Okay, so I don't have that. Negative, negative cancels. I get V of x equals sigma over epsilon naught x. It's a linear function. So it goes up like this. The potential goes up like this. Okay. Don't worry about losing track of the positive and negative signs, you know, initial head of final, that sort of thing. Because at the end, you can always realize, suppose you did make a mistake somewhere, that you got a negative sign, you can always tell yourself, gee, you know, that cannot possibly be right. Because after all, when you are closer to the positive charge, the potential should go up. When you are closer to the negative charge, the potential should go down, right? Suppose you start from here, which is the location of the negative charge, as you move away from it to approach the positive charge, what should happen to the potential? Should go up, right? So if you mistakenly put a negative sign here, you know that cannot be right, because that means the potential would be going down instead of going up. So we get here a linear potential, which corresponds to a constant electric field.